Okay, we're now in chapter 31 from the 9th edition of the textbook. It deals with what's called quantum theory or quantum mechanics. Quantum theory is the theory that describes the micro world, things that are very, very small, and this is what I have made my living at, right, as a scientist, is investigation and research in this area. Okay, so the theory that describes the micro world, the level of atoms, right, and maybe a bit small, a bit larger than atoms as well. But many of the quantities that we experience are granular, not continuous, which means, we'll see what that means. Granular, continuous is where a variable, think of x equals 1.03, right? X can vary in a continuous manner. 1.03, then it can become 1.031, 1.032, and so on. There are no gaps, if you will, because if you want a number that's between 1.031 and 1.032, all you have to do is go to 1.0315, right? Ad infinitum. That is, it's a continuous spectrum, if you will, of numbers. In the case of granular, what happens is, like an x can take only values of 1, 2, 3, 4. It cannot take a value of 1.5. So that's granular. It's like digital in a sense, as opposed to analog. Analog can take any number, range of numbers, whereas digital can only take certain specific states, certain numbers. It can't take the numbers in between, right? So you all know that with digital electronics, how many states are there typically? Digital electronics, you all would probably die if you didn't have your electronics, right? Yep. There's only 2 states. What are the states? Anybody except you?
On and off.
Yes, on and off. Give me numbers.
0 and 1.
0 and 1. You're right. So in digital electronics, everything, like your computer operates on just zeros and ones, right? Yeah, binary. So it adds, subtracts, divides, does all these things with zeros and ones, right? So that would be an example of something that is granular. It is digital as opposed to analog. Okay, examples: particles of light, photons, and particles of matter, such as electrons, exhibit wave as well as particle properties. If you take a baseball and fling it at the wall, it behaves like a... Yes. If you take a baseball and you throw it at the wall, it behaves like a ball, right? Like a solid entity. It doesn't go through the wall. Right? If you ever do an experiment where the baseball goes through the wall without making a hole in it, and we did tape it, you'll probably get a Nobel Prize, right? Now, in the quantum world, you can take a baseball, if you will, a quantum mechanical baseball, and throw it at the wall, and it just disappears. You throw it at the wall, and some fraction of the time, it just disappears. And so, what the heck happened to it? And you go around, and there it's on the other side of the wall. You look at the wall, there's no hole in it. You ask the baseball, how did he get through?
Oh, it vibrated so fast that it passed your mouth.
Extra credit to you, right? You ask the baseball, how did he get through the wall? And the baseball just says, I felt like going through the wall. Did he go through the wall? Did he actually walk through the wall? And says, no, I just reappeared. I disappeared and I reappeared on the other side. And you ask, how did he do this? And the baseball just says, well, there's a certain probability that I could do it, therefore I did it. Which is not any meaningful answer, right? But strange things like this happen in the quantum world. It's kind of like Alice in Wonderland physics.
Wasn't that the guy just won some, not Nobel, I don't know what it was, something like that.
Okay.
For that a thing can be in the same place, like in 2 different spots at the same time. Like it's possible. Like what did they refer it to? The cat thing.
Are you talking about quantum entanglement?
It was this Schrodinger's theory.
Schrodinger's cat?
Yeah.
Or Schrodinger's kitten?
The cat's dead, but the cat's alive. Like,
yes.
It's the same. Like, it's both at the same time.
Yeah, I roll my eyes at that, but go ahead.
Well, I was just saying it wasn't that the guy...
No, I'm not rolling my eyes at you. I'm rolling my eyes at people who insist that the cat is both dead and alive at the same time.
But he just...
They don't know whether it's alive or dead. Okay.
So
right.
he proved that you can be... that an atom could be here and here at the same time, like that it exists in 2 states, total opposite, at the same time. That's what he won it off of. I don't know if you agree or not, but he won his thing off of that.
Yes. In
he proved his theory. Like
in quantum mechanics, let's say that I have a ball, right, that I'm throwing from here to that corner of the room, right? But let's say that this quantum mechanical ball has only two possible routes. One route is this way to there, and the other route is this way to there, right? Very strangely, quantum mechanical experiments indicate that the ball behaves as if, when I throw it from here, I'm trying to throw it from here to there, right? You would think that the ball has to go this way there or this way there. It's not allowed to go this way, right? This way is blocked, but I want to get it there. Strange thing in quantum mechanics is the ball behaves under certain experimental conditions as if that one ball traveled down both paths to reach there. How? Good question, right? Truth of the matter is, like, we have no understanding of how and why these things work. We don't believe the ball is divisible. It cannot be divided into two half balls. So no, it's not as if the ball divided into two half balls, travel and reach there, and then recombine into one ball. So there's some very strange things which make sense, interestingly, from a philosophical perspective, but don't make sense from our conventional science perspective, right? So it seems to be indications of something philosophical, which, okay. Sorry, what? That would be a neat, interesting whole another class, right? So in this lecture, we're just dealing with an overview of quantum mechanics. We won't go into much depth of those things. But any of you are interested are welcome to keep in touch with me after the course, and we can dialogue about such things. Okay, Planck's constant is a fundamental constant which you'll see all over the place in quantum mechanics. It's denoted by this letter H, which relates the energy of a light quantum to its frequency. So E, the energy of the light particle or quantum, is equal to H, that constant, multiplied by F, the frequency of the light. H is given by this value, 6.6 times 10 to the power of minus 34 joule second. We have seen joule before. Joule is the unit of energy, right? So energy second. So energy time, that's the equivalent, right? Or rather the constant. Okay, we introduced the photoelectric effect. Now, explaining this, I have a question for you guys. You're aware that Einstein got the Nobel Prize, right? You're also aware that Einstein is the one who came up with E equals mc square. He's the one who created the general theory of relativity and the special theory of relativity. He's most known for relativity, right? Did he get his Nobel Prize for relativity? He what? He what?
Wasn't it in English, or it was something non-science, wasn't it?
Oh, that's interesting. Maybe it was a Nobel Peace Prize. That's supposed to be a joke. Extra credit to you. Okay, does anybody know what Einstein got his Nobel Prize for? He got his Nobel Prize for explaining the photoelectric effect in the context of quantum mechanics. Einstein also used spent a lot of his career disagreeing with quantum mechanics and its implications, because he did not like the philosophical implications of quantum mechanics. So pretty close to the rest of his career was spent trying to fight quantum mechanics, but he wasn't able to destroy there's too much experimental evidence substantiating the reality of quantum mechanics, right? So, photoelectric effect. Here's a piece of metal connected by a wire to a battery, connected to an ammeter, connected to another piece of metal here, and these two metal pieces are not connected. They are in a glass ampule that's evacuated, right? So, with no light shining on this, there's no current through the system because there's no connection between here and here, right? It's like a switch that's open. So, no current, no voltage. Now what happens is you turn a flashlight onto this, and all of a sudden there's a current. What's going on? It turns out that the photons from the flashlight, they hit the atoms and excite the atoms on this metal plate to give off electrons. So these electrons then travel across this biased, this vacuum, and travel from here to here. They get collected, and you end up with a current, right? So this is called the photoelectric effect. Photo for light, electric for electrons. The emission of electrons from a metal surface when light shines on it. Take a piece of metal, shine light on it, and electrons get emitted. That is the photoelectric effect.
So it wouldn't work in a non-vacuum?
Good question. Extra credit to you. It would work in atmosphere, but what happens is if there's atmosphere present here, these electrons, instead of moving from here to here, they get scattered by the atmosphere. They get scattered, they tend to go back into this, and you don't end up having a measurable current as a result of that, right? Or you need a much higher voltage for that to work. Okay, so photoelectric effect. So here's a piece of metal, flashlight, light coming down on the metal, the light ejects electrons. If you have two flashlights, more light emits more electrons with the same kinetic energy. The electrons, say if the frequency of the light coming from the two flashlights is the same, what happens is the electrons that are coming out have the same kinetic energy. Right? So they come out with the same speed. Now, if you were to change the frequency of the light, right, and make the frequency lower frequency, that means the energy per photon coming from this flashlight is lower. What happens is at some stage, the light does not have enough energy to eject the electrons. So the electrons do not get ejected. However, if you increase the frequency of the light, for the same number of photons coming in, you increase the frequency of light, you end up with the electrons coming off. So let's look at this again. Low frequency, low energy light, no photons. Right? There are photons, but no electrons kicked off. Increase the energy of the incoming light. So you've got 3 photons coming in here. 1, 2, 3 photons coming out. They eject 3 electrons. If I increase the number of these light waves, so instead of 3 photons, I send in 5 photons, you'll end up with 5 electrons getting ejected. However, in this case, because this is a lower energy light, longer wavelength, even if I have 5 photons coming in, no electrons are emitted. Right? Be clear on this. Once we get to the stage so that electrons are emitted, if I double the number of flashlights, then I end up with more electrons being emitted. But this is true only when you have already reached this threshold where the photons are strong enough to kick the electrons out. Yes? So all of this applies only if this is true. This does not apply if that is the case. If the energy of the light that's coming in is not high enough to kick out any electrons, what happens is you can double the flashlights, triple the flashlights, no electrons will come out.
So high enough energy light could cause iron to rust?
Interesting.
In theory, I guess.
Yes. Now rust is basically iron Fe plus O, right?
Right.
Or O2 producing Fe2O3 and Fe3O4, combinations of those, right?
Right.
So if you take a piece of iron and leave it with no moisture in the presence of air, no moisture, just oxygen, what will happen is it will very, very, very slowly rust. If there's moisture, it accelerates maybe catalyzes the process in some fashion, right? Now, some chemical reactions can be accelerated through the presence of light. That is, in chemistry, you probably learned that there is a potential barrier, right? So if you look at the energy with most reactions, you'll end up with the energy plot where the reaction proceeding in some direction, you'll end up with something like this, right? So this is a lower energy. So the compounds want to get down here, and this is the place where they reacted. So like Fe2,3O4. Let's say that this is iron, right? In this spot. What happens is there's an activation barrier. So iron by itself, oxygen comes along, and depending on the height of this barrier, the oxygen may or may not react to the iron. However, if you can overcome this barrier, then the iron atom is able to go over and down here to react and form the iron oxide. Now, going over this barrier can happen through just heating. That's why if you take a substance, paper for instance is very combustible, but it doesn't burn by itself. Notice it's not burning? So paper actually wants to be at a lower, it wants to become carbon and CO2 and all that stuff.
Right.
That happens when it burns. But paper is not, so let's say here's paper, here's the reaction products, carbon and all that stuff. But the paper does not go over because there's an activation barrier. Now the way you get over the activation barrier is putting some energy into it. So cigarette lighter, don't do this. Light one edge of the paper, right? That gets the atoms of the paper, the molecules of the paper that are near the place where it's burning, over this activation barrier to here. Now, coming to the question that you asked, if you send light into a material, there are some reactions that you can get the reaction to proceed by providing the energy to go over this activation barrier from the light that you put in.
So in a sense, it can act as a catalyst for it.
It's like a catalyst. It's not really a catalyst.
Right.
I mean, technically, it's not called a catalyst,
right,
but because in the case of
speed up the process.
Yes, it could. Yeah. Yeah. So colloquially, yes, it's catalyzing the process, but chemically, it is not, because the word means something different, right? Yeah, good point. This explanation is beyond the scope of this class, but I mean this is a good application, right, of these concepts. Cool, good question. Extra credit, right? So, introducing the concept of complementarity, right? Complementarity was enunciated by Niels Bohr, that stated that a particle has its dual aspects. It's like Jekyll and Hyde, Dr. Jekyll and Mr. Hyde, whatever, right? I forget who's the doctor. Now, Jekyll is the doctor? Thank you. Extra credit to you. So, now, a particle has particle properties and wave properties. And depending on the experiment that you set up, you can manifest more of the wave properties or more of the particle properties. So what he's saying basically is that any particle is both wave and particle. They have the complementarity exists. Each of you is partly wave, partly particle. Partly matter, partly wave. So this is an illustration of the behavior of light as particles. How many of you have done darkroom work? As a hobby, 2 of you? Okay? So you probably get a negative, expose your photographic paper, in the darkroom, take the photographic paper and swish it in the tray of chemicals, and you may have noticed over time, right? Initially, you start seeing a little bit of color coming in, right? And then a little more, then a little more, then a little more, a little more, and that's right. And then you know that when you've gotten to the stage, you've had enough exposure to the chemical, then you take it out and rinse it, that kind of stuff, right? And you can stop the process anywhere. This may be after 10 seconds of exposure to the chemical, the washing, whatever. And this may be after 2 seconds, 4 seconds, 6 seconds, and so on. Now, similarly, if you were to take the film and expose it to light. So you're trying to take a photograph of this woman's face, right? So how do you do it? If you were going to take a photo, if you don't mind, take a photograph of your face. Light from the fluorescent lights comes, the photons hit your face and bounce off. So let's say that we've got a camera and it's taking a picture of your face. A few photons coming from there, not bounce off really, but re-emitted or whatever you want to call it, scattered, come off, and they impinge on the film, creating a pattern like this. Do we see a face? No. Do you see how each of these looks like a particle hit it? The photons are behaving as if they are particles coming in, hitting usually a silver nitrate or something of that particle here, and changing its state that then makes it create an image. Increase the number of photons. We can kind of see something is going on. We can't say for sure it's a woman's face. If you didn't know that this is the end product, it would be hard to say that this is going to be a woman's face, right? But knowing that this is the end product, you can kind of tell. Eyes, ear, nose, mouth, right? So increase the number of photons, becomes like this. Now we can see it's a woman's face, but it's not very clear. Keep increasing until you get to this place, right? In this case, what's happening is when enough of the particles of light have bounced off, scattered off, been reflected, whatever you want to call it, off of the woman's face onto the sheet, the photographic sheet, when enough of them have come off, you can see the whole picture of the woman, right? But until this point, the light is behaving like particles. So that's an example of light behaving as particles. We have seen this illustration before. Light now behaving as waves. If you have light waves from a light source like a laser, light source coming to 2 slits, so this behaves like 2 light sources. These waves interfere with each other onto photographic film to create, instead of, if there were no interference, we just get 2 bright lines. Here's a bright line, that's a bright line. So there should be 2 bright lines. However, if light is behaving like waves, these 2 waves interfere with each other, creating constructive and destructive interference, creating this pattern, right? So if you look at the intensity of this, you see these bright spots, dark, bright, dark, and so forth through here, right? So this is an illustration of light behaving as a wave. The previous experiment showed light behaving as a particle. So here's an illustration of light behaving as particles and waves. This is a 2-slit interference pattern, kind of like this, right? 2-slit interference pattern exposed on photographic film. Send a few photons through and we see a pattern that looks like this. We don't see the lines associated with, right, with the interference pattern. So light here is behaving like particles. Increase the number and gradually we see that it's creating a pattern that looks as if light is traveling as waves. Now the strange thing about this is, if you shoot 1 photon through the slit, you get 1 dot. Shoot a second photon separately through the slit, we get a second dot. Shoot a third photon through the slit, you get a third dot. So notice that each time a photon goes through the slit, it's not behaving as a wave, it's behaving as a particle. It's behaving like a single particle. However, when you throw a whole bunch of them, they are interfering with each other, creating this. So individual photons behave as if they're particles, but collectively they're behaving as if they're waves. Really weird, right? Okay, so this is an example of application of this. Now, on the left is a transmission electron microscope. Now, this is what I've done for most of my career, right? This is what my area of expertise is in. Using transmission electron microscopy to analyze materials and problems in industry and all that kind of stuff, right? So I do both research as well as troubleshooting, manufacturing related problems and stuff. So what happens is, like a tool like this, probably now these cost about $1.5 to $2 million. So if you happen to have that money lying around, I'd be happy to buy a TEM and do work for you, right? Stand on the side of the freeway saying, we'll TEM for whatever, right? So here what happens is, we have in this, like the one that I have in my lab, take electrons, accelerate them to 200,000 volts, right? You send them through a bias of 200,000 volts, the electrons travel really fast. As they travel really fast, they travel so fast, they stop behaving like particles. So the electron that we up to this point thought of as a particle starts behaving like a wave. Starts behaving like a wave, and now I can take these electron waves and send them through a sample that I put in here, and I look at what comes out through the sample. And then I can, based on the expertise, based on the patterns that come out, you can get diffraction patterns or interference patterns or absorption patterns, and based on that and your expertise, you interpret what's going on. Very similar in a sense to what happens when you go to the hospital to get if you get an MRI or an X-ray or something, right? So you have your, like the doctor who looks at this, right? Let's say they do an X-ray of your chest, right? And what happens is, so you're looking at your lungs and so on, and to most of us, you look at it and, oh yeah, right? This is like some kind of a hazy image. I see ribs and that's about it. But a person, like a doctor who's expertise in the field, will look at it and say, oh yeah, that is abnormal. See the little dot there? See the little hazy region, right? Which to most of us, I didn't even realize there was a hazy region. Immediately to the doctor it says, it's this kind of cancer or whatever, or it's a cyst, or it's like tuberculosis, or let's do these additional tests. So that kind of expertise is what I have done in industry with materials, right? Using this technique. Now, why do you use electrons rather than light? In a biological lab, you probably use a light microscope, high school and so on, right? With a light microscope, you could look at cells, you could look at bacteria. Bacteria are about 1 to 10 microns in size. 1 micron is about 100th. If you take one of your hair, the width, not the length, the width of the hair is about 100 microns. So you take your hair, divide it 100 times, that's about the size of the smaller bacteria, like about 1 micron. A bigger one could be 5 microns or whatever, or maybe 10 microns, right? So the limit of optical microscopy is about 1 micron, ballpark. If you want to see things smaller than that, you have to go to electron microscopes, where instead of light, you use electron waves which have smaller wavelengths than the light, and so you're able to see things with greater resolution. So this is an example of a mosquito head. Yep, female mosquito head. There are the female's eyes, right? So the eyes of the, I like the response, right? So isn't that like a pretty scary monster? The little thing that comes and lights on you and like sucks your blood, vampire. I'm sorry?
They are monsters.
Yeah, they are, I know. Yeah, I'm so glad we don't have like, we have pretty close to no mosquitoes here, right? Pretty close to. No, I suppose it depends on where you live. But compared to Florida or like Georgia or someplace where there's a lot of moisture, there'll be a lot of mosquitoes, much more than here. Isn't the mosquito the state bird of Texas? I forget. Okay, total joke. Okay, so anyway, so this is with something called a scanning electron microscope, right? So they basically image this by taking an electron probe, and you send electron waves and look at the reflection, right, compile it to get this image. And this has much higher resolution than light. If you try to use this image with light, you would not be able to distinguish these different whiskers and so on. Now, scanning electron microscopy has a lower resolution than transmission electron microscopy. So with a transmission electron microscope, I can actually see atoms. Actually atom columns, but close enough to atoms. So you can take a material, put it into it, and you can actually see the atoms lined up like soldiers, all like in arrays and rows and so forth. That's this, right? So these are practical real-life applications of quantum mechanics that we're learning about. So to you, each of you as individuals, what happens is, anytime, like at some stage, if they were to do a biopsy, right? Let's hope you don't have to be in that situation. But if they were to do a biopsy, a lot of times they would take a little sliver of you and slice it, and they would look at it either in a light microscope or a fluorescent light microscope, or they could then move to higher levels, look at things with scanning electron microscopy. Or if they wanted to look, if you have a bacterial infection, they wanted to look at the bacteria, then they could use either light microscopy, or if with smaller bacteria or with viruses, you'd have to go to transmission electron microscopy. So anytime that you see pictures of viruses, they're taken with a transmission electron microscope, because other microscopes do not have the resolution that you would need to see them, right? So here is an application of electrons as particles and waves. An interference pattern, we saw earlier, we had an example of photons creating an interference pattern, right? Which was an indication with one photon coming through a few photons, you don't see an interference pattern yet, but as you increase the number of photons, you start seeing the fringes, right? So here's the interference pattern, showing that light, if this were light, showing that the light is behaving as waves, and here the light is behaving as particles. So each photon coming through behaves like a particle, but collectively they behave like they're waves. Now, interestingly, when we do the same experiment with electrons, we see the same behavior. An individual electron that's accelerated, that's coming through, behaves like a particle. Increase the number of electrons, and you end up with interference patterns of the electrons, indicating that these electrons are now behaving as waves rather than just as particles. Okay, introducing the uncertainty principle. Now, the uncertainty principle is one of the foundational principles in quantum mechanics. The uncertainty principle basically says that we are uncertain. Right? So, according to the uncertainty principle, what happens is, you cannot know the position and the momentum of the particle with great certainty. So, an application of this, I'm just going to write on the board, is if P is the momentum, delta P multiplied by delta X is greater than or equal to a constant, Planck's constant divided by 2 pi. So this is the uncertainty in the momentum multiplied by the uncertainty in the position. Let's see what this means, like an example of this. Example of this is, every one of you, do you know precisely where you parked your car before you came to class? No? Right? Some of you know that, would you be able to say that it's in the second column, the second row, or do you know it's generally in the, whatever, the south parking lot?
It's in the parking lot. I can tell you exactly where it is.
Sorry, what?
I can tell you exactly where my car is.
Do you have a GPS locator? Or you just know?
I know exactly which spot it's in. I'm parking the same spot every single day.
Okay, so can you tell me its coordinates? I'm not putting you on the spot.
No.
Coordinates in the sense of how many rows and how many columns from here. Let's say that one of these days you counted it. So let's say that you are in row 4, column 37, right? So 437 gives the coordinates of your car, right? So that means the uncertainty of your knowledge of the position of the car is small, because you know precisely where it is, compared to, you said that you don't know where your car is parked, right? So your car, you know that it's parked somewhere in the south parking lot, right? So somewhere in the south parking lot, the uncertainty of the position of your car is the entire dimensions of the parking lot. So in your case, see, the delta is the uncertainty. So delta of the uncertainty here, Jessica, right? Okay. For Jessica, the uncertainty is, let's call it 400 feet along the x-axis, right? For Garen, is it Garen? Okay. For Garen, the uncertainty is much smaller. There still is some uncertainty. And the reason why there's some uncertainty, I'm going to say that the uncertainty of his position of his car is 3 feet, right? And I'll tell you why there's an uncertainty in his position. So you can see that for Garen, the uncertainty is 3 feet. Yes? So that's the delta x. Now the delta p is the uncertainty in the momentum. Is your car moving? Is there uncertainty in the mass of your car? There's some small uncertainty in the mass of your car. There's also small uncertainty in the momentum of your car. Okay, if your car were quantum mechanical, right? So you cannot ever say in quantum mechanics that the particle is absolutely stationary. The reason why on a quantum mechanical level there's uncertainty in the position of your car is because the actual position of the center of your car is the sum, the average of all the positions of all the atoms in your car. So exactly. Extra credit. So think of the car like the stable. The atoms are vibrating back and forth. which means the center of mass of this table is moving around within a certain range. So the actual center of this table, we don't know exactly where it is. There's an uncertainty because at any given instant, a bunch of atoms are here, a bunch of atoms are here, and then an instant later they move back, right? So that center of mass is actually moving around of this table, and similarly of your car. So there's a small uncertainty of the momentum of your car too, because there's a velocity associated with the motion of that center of mass, right? Now this